The water off Cape Cod doesn't forgive mistakes. Neither does war. On a morning in March 1942, Major General Jacob Devers sat in his Washington office, staring at a single sheet of paper that might as well have been written in blood. The numbers didn't lie. Thousands of American soldiers were drowning before they ever fired a shot. Not because of enemy action, because of physics. Because the ocean existed, and Adolf Hitler controlled every usable port from the frozen harbors of Norway down to the sun-scorched docks of Spain. Devers pressed his pen to paper. The letter to Vannevar Bush at MIT came out desperate because desperation was all he had left. We need floating trucks, shipped ashore, no ports. Can your scientists do it? He folded the letter, sealed it, sent it north to Cambridge with the kind of hope that feels dangerously close to prayer. The military establishment had already delivered its verdict. One word: impossible. Trucks belonged on roads where rubber met asphalt and friction made sense. Boats belonged in water where displacement and buoyancy followed rules established before Rome fell. The idea of combining both violated fundamental assumptions about how the world worked. Physics didn't negotiate. Engineering had limits. The generals knew this the way they knew their own names. But Rod Stevens saw water differently. At 35, he'd already won the America's Cup, that most brutal of sailing competitions where understanding how hulls moved through 15-foot swells separated champions from corpses. Stevens didn't just sail boats. He thought in wave patterns and pressure differentials, visualizing flow dynamics with the same clarity other men applied to reading street signs. He knew things about water that no general would ever understand because he'd learned them the only way that mattered, by nearly dying when he got them wrong. Frank Spare brought a different kind of obsession to the problem. The MIT engineer had spent months fixated on something that sounded almost comically trivial until you understood battlefield conditions. He wanted to control tire pressure from inside a moving vehicle. Nobody had ever done it. Nobody had ever needed to. Except that every military truck in 1942 ran on fixed tire pressure, 50 pounds per square inch. Perfect for highways. Absolutely useless for sand. Completely worthless in mud. Spear's laboratory looked like a madman's workshop. Every surface covered in sketches of rotating seals and pneumatic lines and dashboard controls that existed only in his mind. He saw what others missed, that the difference between a truck that moved and a truck that died could be measured in pounds per square inch. Dennis Pulliston completed the unlikely trio with credentials earned in storms that would have killed softer men. The British deep-water sailor had crossed the Atlantic in vessels smaller than most people's living rooms, developing an instinct for what kept things floating when every rational calculation said they should sink. Pulliston approached design with the cold practicality of someone who knew that equipment working perfectly in a laboratory often failed catastrophically when salt spray and engine vibration and 6-foot waves started their brutal work. His job was translation. Taking Stevens' yacht racing theories and Spear's mechanical dreams and turning them into something that would actually function while people were shooting at you. 3 civilians, 38 days, one impossible idea. They were about to prove something the generals didn't want to hear, that American trucks could float, that the right kind of innovation could determine whether D-Day succeeded or failed so catastrophically that historians would still be calculating the body count 100 years later. The Mahogany Conference, table at MIT's Office of Scientific Research and Development, had borne the weight of America's most desperate problems since the war began. Vannevar Bush spread Devers' letter across the polished surface that morning, his fingers tracing handwriting that carried the urgency of men dying in surf they couldn't cross. The question hung in the Cambridge air, like pipe smoke. Can your scientists do it? Bush understood the mathematics of amphibious warfare better than most generals because he'd studied the numbers that military men preferred to ignore. Every landing craft cost $10,750. Enough to buy 3 Sherman tanks, enough to equip an entire infantry company with everything they needed to stay alive. Yet these expensive vessels could only dump their cargo at the waterline, forcing soldiers to carry ammunition and medical supplies across hundreds of yards of open beach, while German machine gunners picked them off from concrete bunkers that had been designed specifically for this purpose. The ancient problem had killed more Allied troops than German bullets. How do you move 5,000 pounds of critical supplies from ship to inland ammunition dump when the enemy controls every port that matters? The solution required thinking that military minds simply couldn't produce. Minds trained in rigid categories: land warfare, naval combat, doctrine that said trucks belonged on roads, and boats belonged in water and never shall the two meet. Bush needed civilians, men who had never learned the rules, who might see possibilities where training saw only impossibility. Rod Stevens answered Bush's call on a Tuesday morning. He arrived at the Cambridge office with the quiet confidence of a man who just won the most prestigious yacht race in the world. That kind of confidence doesn't announce itself. It simply exists. Stevens possessed an understanding of water that went beyond mathematics into something closer to instinct. He could visualize how a properly designed vessel would cut through heavy seas without losing cargo or crew. Could see in his mind's eye the flow patterns and pressure differentials that killed amateur sailors and made champions. The principles that governed yacht racing applied to military logistics with deadly precision. Displacement, stability, hydrodynamic efficiency. Words that sounded academic until you realized they meant the difference between soldiers who lived and soldiers who drowned. Frank Spire arrived from MIT's Mechanical Engineering department carrying a portfolio that covered every surface in his laboratory. The reserve officer had been obsessing over his tire pressure problem for months. Most engineers thought it trivial. Anyone who understood battlefield conditions recognized it as revolutionary. Spear's diagrams showed rotating seals and air pressure systems and dashboard controls that had never been successfully integrated because nobody had ever needed them. Badly enough to solve the 1,000 small problems that stood between concept and reality. In 1942, every military vehicle operated with fixed tire pressure, 50 pounds per square inch for highway driving, which meant certain failure in sand, guaranteed disaster in mud. Spear envisioned a system that could adjust from 50 psi on concrete roads to 12 psi for beach operations without stopping the vehicle, without requiring soldiers to manually adjust individual wheels, while enemy artillery turned them into scattered pieces of meat and bone. A mechanical innovation that would become standard on every military truck produced for the next 80 years. If it worked, Dennis Pulliston completed the team with credentials spanning 2 continents and countless storms that should have killed him, but didn't. The British sailor had developed an understanding of what kept boats afloat when physics and common sense suggested they should sink to the bottom and stay there. Pulliston approached every design decision with life-or-death practicality, not because he was dramatic, because he'd seen equipment that worked perfectly in laboratory conditions fail catastrophically the moment salt spray and engine vibration started doing their work. His role demanded integration, taking Stevens' theories and Spear's innovations and making them function together as a unified system that would work flawlessly under enemy fire. Or admit failure and watch soldiers die because the engineering wasn't good enough. The timeline Bush established defied every conventional military procurement procedure ever written. April 21st, contracts signed with General Motors. April 24th, wooden mock-up construction begins with teams working through weekends. April 27th, scale model completed for initial testing. May 30th, first prototype ready for water trials. 38 days from conceptual sketches to floating vehicle. Based on GMC's proven CCKW chassis, the 2.5-ton Deuce and a half, already trusted by every infantry division in the European theater. the truck that was about to learn how to swim. Stevens designed the hull with the same precision he'd applied to winning the America's Cup. Welded steel construction, flat bottom, ribbed sides for stability in heavy seas, 31 feet long, 8 feet wide. The dimensions weren't arbitrary. They maximized cargo capacity while maintaining seaworthiness, sacrificing nothing to accommodate the dual-purpose design. His calculations showed that proper weight distribution would allow the vehicle to carry 5,000 pounds of ammunition, or 25 fully equipped soldiers from transport ship to inland supply depot without requiring pier facilities or artificial harbors or any of the infrastructure that took months to build and gave the enemy convenient targets. Speer's tire pressure innovation represented the project's most revolutionary element because it solved a problem nobody else realized existed. His system employed dashboard-mounted controls, pneumatic lines, rotating wheel seals that maintained air pressure while allowing wheels to turn freely. The mathematical precision required to balance airflow and mechanical reliability and combat durability had never been achieved in automotive engineering. Yet Speer's prototype demonstrated flawless operation. 50 psi for highway speeds, 25 psi for rough terrain, 12 psi for sand operations, all controlled by a simple lever beside the driver's seat. Simple for the operator, impossibly complex for the engineer who had to make it actually work. Puliston's contribution ensured that brilliant individual innovations worked together instead of fighting each other. His propeller and rudder design provided 5.5 knot speeds in calm water while maintaining steerage in conditions that would swamp conventional landing craft. The mechanical integration of automotive transmission and marine propulsion and steering systems required expertise that bridged civilian maritime experience with military operational requirements. Required understanding how systems failed under stress, how salt water corroded metal, how engine vibration loosened bolts, how 6-foot waves tested every weld and joint with forces that laboratory equipment couldn't simulate. The initial Army demonstration met with predictable skepticism. Career officers trained to evaluate equipment within established categories couldn't envision how a vehicle that violated fundamental assumptions could provide military advantage. Too complicated, summarize the official rejection. Trucks belong on roads, boats belong in water. The DUKW faced bureaucratic extinction before proving its revolutionary potential. Designated for its production year. D for 1942, U for amphibious capability, K for all-wheel drive, W for dual rear axles, a name that sounded like a duck's quack, which became exactly what soldiers called it, the duck, the truck that swam. One final demonstration remained. Provincetown, Cape Cod. December 1942. 90 officers invited to witness what might be the vehicle's last operational test. Then nature intervened with a storm that would transform skepticism into desperate necessity, proving that impossible innovations sometimes save lives when conventional wisdom fails completely. The weather forecast for December 3rd promised calm seas and light. Winds across Cape Cod Bay, perfect conditions for demonstrating an untested amphibious vehicle to 90 skeptical Army officers who'd already decided it wouldn't work. Instead, meteorological chaos descended on Provincetown with the fury of a North Atlantic hurricane. 60-mile-per-hour winds drove 15-foot swells against the Massachusetts coastline. The scheduled DUKW demonstration transformed from routine equipment evaluation into something else entirely. A test written by God, or chance, or whatever force decides when theory meets reality, under conditions that expose every design flaw with lethal consequences. Coast Guard Cutter Jackson, 75 feet of welded steel hull, commanded by experienced mariners who'd weathered dozens of nor'easters in these exact waters. They knew every sandbar, every current, every threat that these waters posed to small vessels in heavy weather, yet the storm's violence exceeded their experience, and their equipment's limits both. Mountainous seas drove the Jackson onto a sandbar 200 yards offshore. her steel hull grinding against sand with each wave that lifted and dropped her 6.5-ton weight like a toy. Radio transmissions grew increasingly desperate. The cutter was breaking apart under forces no vessel her size could withstand indefinitely. Physics doesn't care about experience or training or how many storms you've survived before. Conventional rescue operations failed with mechanical precision. Coast Guard motor lifeboats designed specifically for rough water rescues turned back after their crews determined that approaching the Jackson would result in additional casualties rather than successful evacuation. The 36-foot vessels, powered by reliable diesel engines and crewed by men who'd saved hundreds of lives in similar conditions, simply could not penetrate waves that towered above their pilot houses and threatened to roll them completely over. Sometimes the sea says no. Sometimes courage isn't enough. Navy crash boats attempted the rescue with equipment designed for recovering downed aviators in combat conditions. Their shallow draft hulls and powerful engines normally provided advantages in surf operations, but the storm's intensity overwhelmed their capabilities. Each attempt to approach the Jackson resulted in dangerous broaching as crosswaves caught boats broadside, forcing crews to retreat before their own vessels joined the cutter on the sandbar, adding more bodies to count instead of subtracting them. Beach-launched rescue craft faced immediate disaster. Local fishing boats normally capable of handling rough seas swamped within minutes of entering the surf. Their experienced crews recognized conditions that exceeded safe operational limits. The mathematical relationship between wave height and small boat survival had reached the point where physics, not seamanship, determined outcomes. 7 Coast Guardsmen remained trapped aboard the disintegrating Jackson, their radio calls providing increasingly urgent updates on structural failure. She's breaking up fast. Static-filled transmissions that reached the Provincetown demonstration site where 90 Army officers watched conventional rescue methods fail systematically. Professional mariners with all the training and equipment that military doctrine considered adequate could only wait for death as their vessels split apart. Beneath them, Rod Stevens observed the unfolding tragedy with the analytical mind that had won. Yacht races through superior understanding of extreme weather sailing. The conditions that defeated conventional rescue craft represented exactly the operational environment for which he designed the DUKW. 15-foot seas, 60-mile-per-hour winds, surf conditions that prohibited normal boat operations. The perfect test. We'll take the DUKW, he announced to the assembled officers, transforming the demonstration from theoretical equipment evaluation into practical life-saving mission, into proof or failure with no middle ground. Stevens' crew loaded quickly. Marine photographer Stanley Rosenfeld joined the mission to document everything, understanding that the rescue attempt would either validate or destroy the DUKW program permanently. Several engineers whose theoretical calculations had contributed to the vehicle's design now faced the ultimate test of their work. Emergency rescue equipment, medical supplies, communications gear, everything loaded into the 6.5-ton amphibious truck that was about to either save 7 lives or add more bodies to the count. The DUKW roared down Provincetown Beach at 50 miles per hour, 6-wheel drive and low-pressure tires providing traction that conventional vehicles couldn't achieve on sand, softened by wind-driven spray. Stevens maintained highway speed until the final moment, then drove directly into mountainous surf that had defeated every other rescue attempt. The transition from land to sea operation occurred at full speed, automotive transmission disengaging, marine propeller drive engaging with mechanical precision that Speer's innovations had made possible. 5.5 knots through conditions that challenged vessels 3 times the DUKW's size. Hydrodynamic design principles that Stevens had perfected through decades of competitive sailing. The flat-bottomed hull rode over waves rather than cutting through them. Ribbed sides provided stability that prevented dangerous rolling. Pulston's propeller and rudder systems maintained steerage despite seas that would have overwhelmed traditional small boat designs. The rescue operation required seamanship that combined yacht racing, precision with combat zone urgency. Stevens maneuvered the DUKW alongside the foundering Jackson, while both vessels rose and fell through wave cycles that threatened catastrophic collision. Heavy seas crashed over both hulls, flooding the DUKW's cargo compartment, testing watertight integrity that determined survival for rescuers and victims alike. One by one, Stevens' crew pulled 7 Coast Guardsmen aboard, completing the evacuation just as the Jackson's hull finally surrendered to forces that had been destroying her for hours. The return journey to Provincetown Beach proved the DUKW's complete amphibious capability. Loaded beyond normal capacity with rescued personnel and emergency equipment, the vehicle maintained speed and stability through seas that continued threatening conventional rescue craft. The transition from marine to land operation occurred seamlessly. Propeller drive disengaging, 6-wheel automotive drive resuming, carrying everyone safely up the beach to waiting medical personnel and astonished Army observers who just watched the impossible become routine. Rosenfeld's photographs captured every moment, from the initial surf entry to the final beach landing. Within hours, he boarded the next train to Washington, carrying visual proof that the impossible vehicle had accomplished what no other equipment could achieve. The dramatic images would reach high-ranking military officials within 24 hours, transforming bureaucratic skepticism into urgent procurement orders that would change the course of amphibious warfare forever. 7 men were alive who should have been dead, because 3 civilians had ignored what everyone knew was impossible. Rosenfeld's photographs reached the Pentagon within a day, carried by express train through a winter landscape that seemed peaceful compared to the storm-lashed Cape Cod coastline. The images told a story that no amount of technical specifications or theoretical arguments could convey. 7 Coast Guardsmen breathing because an impossible vehicle had accomplished what conventional rescue craft could not. Major General Jacob Devers possessed irrefutable evidence that his faith in civilian innovation had been justified. The photographs circulated through military headquarters with unprecedented speed, reaching decision-makers who dismissed the amphibious truck as an expensive experiment. Each image documented specific moments: the DUKW driving into mountainous surf, maneuvering alongside the foundering Jackson, evacuating 7 men who would have died without this revolutionary intervention. Visual evidence that eliminated bureaucratic debate about theoretical capabilities, replacing abstract engineering discussions with concrete proof of life-saving performance under extreme conditions. October 1942 brought official adoption. Mass production contracts awarded to General Motors plants in St. Louis, Missouri. The decision represented complete reversal of military thinking that had previously rejected the vehicle as unnecessarily complex. Devers' endorsement carried the weight of successful field testing supported by photographic documentation that no staff officer could dismiss. The production numbers reflected America's industrial capacity operating at wartime intensity. By the end of 1942, first production units rolled off assembly lines that had been converted from civilian automobile manufacturing to military vehicle production. The St. Louis facility, previously known for producing Chevrolet sedans and Buick coupes, now focused entirely on welding steel hulls and installing marine propulsion. Systems designed by 3 civilians who'd revolutionized amphibious warfare in 38 days. 1943 witnessed unprecedented manufacturing acceleration as military planners recognized the DUKW's strategic importance. 5,000 units emerged from General Motors facilities, each vehicle representing $10,750 of precision engineering that combined automotive reliability with marine capability. Production line workers, many of them women who'd replaced male employees serving in combat units, mastered complex assembly procedures required to integrate Stevens' hull design, Spear's tire pressure system, and Puliston's propulsion components into unified amphibious vehicles. The St. Louis plant achieved peak production during 1944, delivering 10,000 DUKWs as Allied forces prepared for the largest amphibious operation in military history. Manufacturing process required coordinating dozens of subcontractors producing specialized components. Marine propellers from Michigan, steel hulls from Pennsylvania, tire pressure control systems from Massachusetts. Each vehicle demanded quality control standards that exceeded civilian automotive requirements, since failure in combat conditions meant death rather than inconvenience. The final production tally reached 21,137 vehicles, the largest procurement of specialized amphibious equipment in military history. Each DUKW cost the equivalent of $170,000 in contemporary purchasing power, making total program investment exceed $3.6 billion. The expenditure reflected military recognition that revolutionary innovations often required substantial financial commitment to achieve strategic advantage, money that would be measured not in dollars, but in lives saved. Beaches secured, battles won. Sicily provided the DUKW's first combat test during Operation Husky in July 1943. Allied forces faced the familiar amphibious warfare problem: how to maintain supply lines from offshore transport ships to inland ammunition dumps when German forces controlled all port facilities. Traditional landing craft could deliver cargo to beach landing sites, but required separate vehicles to transport supplies 20 miles inland to forward operating bases, where infantry and artillery units desperately needed ammunition, medical supplies, replacement equipment. The DUKWs eliminated this critical vulnerability by driving directly from ship to supply depot without stopping at the waterline. Each vehicle carried 5,000 pounds of essential cargo across beaches that remained under intermittent German artillery fire, then continued inland through terrain that stopped conventional trucks. The operational advantage proved immediately apparent. Supply lines that previously required multiple transfers and exposed beach operations now functioned as single-vehicle missions that reduced casualty rates and increased delivery efficiency. Combat performance exceeded theoretical projections in every measurable category. DUKWs operated successfully in surf conditions that prevented normal landing craft operations, maintaining supply flow during rough weather that traditionally suspended amphibious operations. Their six-wheel drive capability handled soft sand and muddy terrain that immobilized standard military trucks, while the tire pressure control system allowed instant adaptation to changing ground conditions without stopping to manually adjust individual wheels. The vehicles proved equally valuable for casualty evacuation, reversing their normal supply mission to transport wounded soldiers from forward positions to hospital ships anchored offshore. This dual-purpose capability eliminated the need for separate medical evacuation systems, simplifying logistics, coordination while providing critically wounded personnel with faster access to surgical facilities that could save their lives. German forces initially couldn't understand how Allied supply operations continued functioning despite successful interdiction of traditional beach landing sites. Intelligence reports from captured documents revealed confusion about American logistics capabilities that seemed to violate basic assumptions about amphibious warfare limitations. The DUKWs operated so differently from conventional landing craft that German tactical doctrine provided no effective countermeasures for vehicles that could transition seamlessly between land and sea operations. They were fighting an enemy that refused to follow the rules. By the end of 1943, DUKW production had reached full capacity. Military planners prepared for Operation Overlord, the cross-channel invasion that would determine whether Allied forces could establish permanent foothold in Nazi-occupied Europe. Sicily had demonstrated tactical capabilities. Normandy would test whether Stevens' Spear and Puliston's revolutionary design could handle strategic-scale operations involving hundreds of thousands of troops and millions of tons of supplies. The stage was set for ultimate validation of an impossible idea that had transformed from desperate experiment into indispensable military capability. Operation Overlord demanded logistical precision that exceeded any previous military undertaking in human history. 2,000 DUKWs received assignment to the cross-channel invasion, strategic deployment calculated with mathematical accuracy that reflected the operation's dependence on sustained supply flow. 12 companies would support Omaha Beach operations where German defensive positions threatened to annihilate Allied forces before they could establish permanent foothold. 7 companies would reinforce Utah Beach, where paratroop units required immediate resupply to maintain precarious inland positions. Each DUKW carried 5,000 pounds of ammunition, medical supplies, artillery shells that would determine whether 150,000 Allied soldiers survived their first day on Nazi-occupied soil. The vehicles represented America's industrial mobilization concentrated into amphibious form. St. Louis assembly lines had produced these specific units during spring 1944. Each DUKW incorporating lessons learned from Sicily combat operations. Stevens' whole design had been refined based on field reports about stability in rough seas. Spear's tire pressure system now included backup controls that prevented complete failure if primary mechanisms suffered battle damage. Puleston's propulsion components featured improved corrosion resistance after exposure to Mediterranean saltwater revealed maintenance vulnerabilities. Every lesson written in blood had been translated into engineering improvements. June 6, 1944 brought meteorological conditions that nearly cancelled the largest amphibious operation in military history. General Eisenhower faced impossible weather predictions. Storms in the English Channel that would swamp conventional landing craft, winds that would scatter paratroop formations, seas that violated every safety protocol for amphibious operations. Yet delaying the invasion meant losing tidal conditions that wouldn't recur for weeks, potentially allowing German forces to strengthen Atlantic wall defenses beyond Allied capability to penetrate. Key hour arrived at 6:30 a.m. First wave of assault troops hitting Normandy beaches through surf that challenged every assumption about amphibious warfare. Feasibility, German artillery, and machine gun fire created killing zones that stretched from waterline to bluffs above Omaha Beach. Concrete, bunkers housed weapons positioned to destroy any vehicle or soldier attempting to cross open sand. Initial landings achieved tactical surprise, but faced immediate annihilation unless supply lines could deliver ammunition and reinforcements faster than German defenders could coordinate counterattacks. DUKWs followed 30 minutes behind assault waves, engines roaring across the English Channel, propellers churning through seas that would have defeated conventional vessels. The amphibious trucks approached Normandy beaches carrying ammunition and medical supplies that would determine whether the beachhead could survive its first critical hours. Each vehicle represented a logistical lifeline between offshore transport ships and forward, positions where infantry units faced German counterattacks with rapidly diminishing ammunition supplies. The transition from sea to land, operations occurred under direct enemy fire. DUKWs drove through surf zones that German artillery had pre-sighted for maximum destruction. Machine gun bullets sparked off steel hulls. Mortar shells exploded in fountains of sand and seawater that obscured visibility and tested driver navigation skills. The vehicle's 6-wheel drive engaged as they climbed Omaha Beach, low-pressure tires providing traction on sand that stopped conventional trucks, carrying essential supplies toward ammunition dumps located beyond German observation posts. Men died around them, above them, behind them. The DUKWs kept moving because stopping meant everyone died. The first 24 hours of Operation Overlord witnessed logistical performance that exceeded every theoretical projection. DUKWs moved 3,000 tons of critical supplies during the invasion's most vulnerable period, when German forces concentrated maximum firepower against Allied beachheads that remained within artillery range. Traditional landing craft would have required artificial harbor construction before achieving comparable supply flow, a process that typically consumed 6 months and left invasion forces dependent on equipment delivered across exposed beaches. The week following D-Day demonstrated the DUKW's strategic importance as supply operations expanded to support 150,000 Allied troops advancing inland from initial beachheads. 15,000 tons of ammunition, fuel, food, replacement equipment moved through the amphibious supply system. While German forces attempted to contain Allied breakout operations, each vehicle completed multiple round trips between offshore transport ships and forward supply depots, maintaining delivery schedules that kept combat units supplied despite enemy interdiction efforts. The first 90 days of Normandy operations established unprecedented logistical statistics that would define amphibious warfare for subsequent decades. 340,000 tons of supplies flowed through the DUKW system. Everything from individual rifle cartridges to complete artillery pieces that enabled Allied forces to advance beyond initial beachheads. The tonnage figures reflected not just material movement, but strategic capability that allowed relatively small invasion forces to defeat larger German defensive armies through superior supply efficiency. Weather nearly destroyed the invasion during the June 19th to 22nd storm period. Meteorological conditions exceeded any previous recorded measurements for the Normandy coastline. Winds reached hurricane strength. Waves demolished Mulberry A, the artificial harbor that military planners had considered essential for sustained supply operations. Traditional landing craft became unusable. The storm created surf conditions that violated every safety protocol for conventional vessel operations. DUKWs continued operating throughout the 4-day tempest that threatened to sever Allied supply lines completely. Their unique design characteristics enabled continued operations when weather eliminated every alternative supply method. Stevens' stable hull configuration, Speer's adaptive tire pressure system, Pulston's reliable propulsion components, 6-wheel drive handled soft sand created by constant rainfall. Amphibious capability maintained access to offshore transport ships despite surf conditions that prohibited normal landing craft operations. The hidden crisis revealed the DUKW's most critical strategic value: operational flexibility that functioned regardless of weather conditions that traditionally suspended military operations. German forces had planned their defensive strategy around weather patterns that would periodically isolate Allied beachheads from offshore supply sources. The storm's timing seemed to validate German expectations about amphibious warfare vulnerabilities. Yet DUKW operations continued uninterrupted, while conventional logistics systems failed completely. Combat effectiveness during the Normandy breakout period proved that logistics determined battlefield outcomes as decisively as firepower and tactical innovation. Allied forces advanced inland because their ammunition never ran out. Their wounded received medical treatment. Their equipment remained functional through consistent supply flow that German forces couldn't interdict. The DUKW system had transformed theoretical supply planning into practical, strategic advantage that enabled military victory through superior engineering rather than superior numbers. May 8, 1945 arrived with German surrender documents signed in a schoolhouse in Rennes, France, ending the European war that had consumed 6 years and 60 million lives. Final logistics tallies revealed numbers that military historians would study for decades. DUKWs had moved 5,500,000 tons of the 15,750,000 tons of Allied supplies delivered to European battlefields. 1/3 of everything that enabled victory had traveled through the amphibious supply system that 3 civilians had, created in 38 days during spring 1942. The statistical achievement represented more than tonnage figures. Each pound of supplies delivered by DUKW had replaced conventional logistics methods that required artificial harbors, multiple vehicle transfers, extended supply lines vulnerable to enemy interdiction. Traditional amphibious operations would have demanded 6-month harbor construction projects before achieving comparable supply flow rates. Delays that would have allowed German forces to strengthen Atlantic wall defenses beyond Allied capability to penetrate successfully. Rod Stevens' hull design had proven seaworthy enough to cross the English Channel, fully loaded under combat conditions, validating yacht racing principles applied to military logistics with mathematical precision. The flat-bottom configuration with ribbed sides had handled 15-foot seas while carrying maximum cargo loads, demonstrating hydrodynamic efficiency that conventional landing craft couldn't match. His calculations about weight distribution and stability had saved thousands of lives by ensuring fully loaded vehicles remained controllable in surf conditions that would have swamped traditional amphibious equipment. Frank Spur's tire pressure innovation had become the detail that changed everything. About military vehicle design, the dashboard controlled a system that adjusted from 50 pounds per square inch for highway operations to 12 psi for beach work had eliminated mobility, limitations that previously confined military trucks to prepared roads. Every vehicle produced since 1945 incorporated variations of Spear's rotating seals and pneumatic controls, making his 38-day invention a permanent feature of automotive engineering that extended far beyond military applications. Dennis Pilliston's integration of propeller and rudder systems had created marine propulsion that functioned reliably in combat conditions rather than laboratory environments. His deep-water sailing experience had translated into mechanical components that survived salt spray, engine vibration, crushing impact of heavy seas while maintaining 5.5-knot speeds essential for tactical mobility. The propulsion systems had operated flawlessly through Mediterranean campaigns, Atlantic crossings, Pacific operations that tested every design assumption about amphibious vehicle reliability. The three innovations perfected during Frantic Spring 1942 had created synergistic capabilities that exceeded the sum of individual components. Stevens' hull provided the platform for Spear's adaptive mobility system. Pilliston's propulsion enabled both designers' concepts to function in maritime environment that defined amphibious warfare. Successful integration had required civilian thinking, unconstrained by military doctrine about separate land and sea vehicle categories. 21,137 DUKWs had rolled off St. Louis assembly lines during the war's peak production period, each vehicle representing industrial mobilization, focused on revolutionary innovation rather than conventional military equipment. Total program cost of $3.6 billion had purchased strategic capability that traditional procurement methods couldn't have achieved regardless of financial expenditure. No amount of conventional landing craft could have provided operational flexibility that enabled sustained supply flow. During the Normandy storm period, when weather eliminated every alternative logistics method, most vehicles faced immediate scrapping after Germany's surrender, victims of military budget reductions that prioritized demobilization over equipment preservation. The amphibious trucks that had enabled victory became surplus inventory sold to civilian buyers who recognized their utility for construction projects and emergency services. Thousands of DUKWs disappeared into scrap metal dealers who valued their steel content more than their revolutionary engineering, erasing physical evidence of innovation that had changed warfare's fundamental assumptions. The three designers returned to civilian careers with minimal public recognition for achievements that had influenced military history's course. Stevens resumed yacht racing, applying lessons learned from military hull design to competitive sailing that continued producing championship victories. His America's Cup experience had prepared him for the DUKW project, but wartime innovation enhanced his understanding of hydrodynamic principles that separated winning designs from mediocre attempts. Pilliston authored sailing books that shared deep-water navigation techniques with recreational mariners, translating combat-tested seamanship into civilian applications that improved small boat safety. His wartime integration work had required mastering mechanical systems beyond traditional sailing expertise, creating knowledge that benefited both military and civilian maritime communities through publications that remained standard references for decades. Spear continued, inventing military innovations that solved operational problems through mechanical engineering excellence. Though none achieved the strategic impact of his tire pressure control system, his subsequent patents covered vehicle suspension systems, communications equipment, specialized tools that improved military effectiveness through attention to details that other engineers overlooked or dismissed as unimportant. The Korean War's outbreak in 1950 brought DUKWs back to combat status for the Incheon landings. Their amphibious capability again proved essential for establishing beachheads without port facilities. The vehicles that had enabled D-Day success demonstrated continued relevance in different theaters against different enemies, validating design decisions made 8 years earlier by 3 men who'd ignored conventional wisdom about military vehicle limitations. Contemporary legacy appeared in unexpected forms throughout American cities, where duck tours carried tourists through downtown streets and harbor waters using the same basic design that had won World War II. The recreational applications demonstrated civilian recognition of engineering, excellence that transcended military origins, proving that revolutionary innovations often found new purposes beyond their original requirements. Speer's tire pressure system became standard equipment on every military vehicle produced after 1945, from jeeps to main battle tanks, ensuring that his 38-day The Innovation influenced military mobility for subsequent generations. The mechanical principles he'd pioneered under wartime, pressure became foundational technology that improved vehicle performance in conditions ranging from desert, sand, to Arctic tundra. The lesson embedded in their achievement extended beyond military applications to fundamental questions about innovation and institutional thinking. 3 men had ignored expert opinion, challenged conventional wisdom, created the impossible through civilian approaches to military problems. Their success proved that revolutionary thinking often came from outsiders who lacked professional training that taught others why new ideas couldn't work, enabling breakthrough innovations that experts considered theoretically impossible but practically essential. Maybe they didn't fully realize it then, standing in that Cambridge office in spring 1942. But they were rewriting rules that had governed warfare since humans first learned to build boats and roll wheels. They were proving that the distance between impossible and inevitable could be measured in 38 days. If you had the right minds, the right problem, the right moment when desperation forced innovation, past every bureaucratic barrier that normally killed new ideas, before they could prove themselves, long after the smoke cleared and the last veteran passed, and the tourists climbed aboard, refurbished DUKWs for harbor tours, one truth remained. 7 Coast Guardsmen had lived because 3 civilians refused to accept that trucks belonged on roads and boats belonged in water. And 150,000 Allied soldiers had crossed Normandy beaches with enough ammunition to stay alive because those same 3 men had 38 days to prove the impossible. The water off Cape Cod still doesn't forgive mistakes, but sometimes, on rare days when genius and necessity and courage align perfectly, it forgives impossible dreams and lets them float